Go ahead, say something. You wanted to say something?
Yeah, your share screen, they're like these big gray blocks just
Oh,
that blocking
thanks.
a part of it.
Yeah, yeah.
Uh, you don't see recap here?
Well, now there's only one gray block, but it's on the side, above the P.
Uh, so, I mean, the current slide just has got one word on it called recap. You don't see that?
I can see the recap. Yeah.
Ah, perfect. So, yeah, please, of any technical problems, immediately let me know. All right. Um,
Wait, now there's another gray block again.
oh, I see.
Now it's blocking half a recap. Okay, now it's on the side. But I can still see most of yeah.
Okay, okay. So I think I know what you're saying. Okay, just give me 1 minute. Yeah, maybe this one has some issues. Hmm. Give me 1 second. All right. How about now? Can you guys just see the recap thing?
No, there's still like one block that's above the A and P.
Oh, cool. Thanks for letting me know. How about now?
Yeah, now I can see recap.
Perfect. Thank you very much. Okay, off we go now. Sorry again for the delay. So yeah, I have started recording this. Um, so yeah, we discussed words in general and some words of mathematics in particular. Um, we talked about this particular notation. I mean, I hesitate calling it a symbol, but it's more like a notational convenience. You obviously know that this stands for and so on, or it really doesn't stand for infinity, but we just say, there's an important distinction here, and we'll come to that. So we started with this particular question, or we talked about this question. Are these two numbers the same? And then Apurva asked one question. If 0.999 dot 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 is not the same as 1 or is less than 1, what is the number that is between those two numbers? How about this number? Isn't this number in between those two numbers? Because if we add 0.999, not really in between, I'm just saying that you add this number 0.000 dot dot dot, then 1 to the number 0.999 dot dot dot, won't we get 1? Yeah, go ahead. Whoever has raised the
Yes, so I think that that wouldn't be the case because if you have put a 1 at the end, that would inquire that the number that you've written below is finite, but the number above that is infinite because you have put three dots after the original number and then put nothing at the end. So I don't think that's the case.
Yeah, so I think you're absolutely right. This number that we have here, 0.000 dot 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 1, how would we translate that in words? It would be 0 point and followed by an infinite number of zeros and then 1. Now that makes no sense because if we have infinite number of zeros, then there is infinite number of zeros. There's nothing, won't be able to exhaust that list to get to this parent last one. So what I'm trying to do here is that, trying to convince you that these two numbers are the same. And it is perfectly fine if you initially are not convinced. Hopefully we will have more arguments for you to look at. So here is another argument. So would you agree that this number 0.999 dot 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 is made up of these two numbers 0.909090 dot 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 and 0.090909 dot dot dot,
Yes.
right? You agree with that? I like that spontaneous yes. Anybody who disagrees with that?
Yeah, I agree with it.
Cool. I believe that pretty much everyone does that. So now what is the first one of these numbers? What number is that? Can you tell me that number in terms of, since this is a decimal fraction, we have reasons to believe that I can express it as a simple fraction, a divided by b or a by b, right? What is 0.909090 dot dot dot? Which simple fraction, a by b, has this value same as this value? It's definitely bigger than 9 by 10, right? Because
Is
9 by
it
10,
is it 10 by 11?
very good job. So that's right. So it is 10 by 11. And what about 0.090909 dot dot dot?
It's I think 1/11.
Nice. Now what happens? We said that these two numbers, the decimal fractions, add up to 0.999 dot dot dot. What happens to the addition of their simple fraction equivalents? 10 by 11
One.
plus 1 by 11, the same denominator. You add the numerators, you get 11 by 11, which is
One.
1. So isn't it convincing enough an argument? I believe so. Not because I have done that, but because it is. So what I'm trying to tell you here is that these two numbers, we have got to agree upon this. And by the way, before I move on from this, I've got a side question for you. What makes the decimal representation of a fraction like 1 by 8 or 1 by 25 terminating, whereas that of a fraction like 1 by 6 or 1 by 7 or 1 by 11 or 10 by 11 non-terminating? Have you guys ever wondered about that? We see 3 by 4 is equal to 0.75. We say 1 by 4 is 0.25. But what about 1 by 11, just like this one? This doesn't terminate. So what dictates it? It's a question for you guys to take back and think about. I think Yeah, that was my side question. So please think about it. What makes something a terminating decimal and a non-terminating decimal?
I think anything that is divided by a multiple of, I don't know, 2 or 5 will make it divisible. Like
Hey, can you
squares
be
of
more a
2
little
and
more precise? I think you're on the right
like
track. You're on the
like
right track.
squares of 2, squares cubes to the power 4 of 2, and similarly with 5, like 5, 25, 125, that way.
Yeah, I think that is a good observation. So if the denominator is of the form 2 to the power m, 5 to the power n, then it will be a terminating decimal, not otherwise. And it is true only in the decimal system. If you have a binary system, then what happens? This is a fascinating thing, I mean, this goes into what we call arithmetic or number theory, but these are the questions that we all should be pondering about. If all I have is a binary zeros and ones, not the 10 digit, but just the 2 bits, 0 and 1, in that case, what happens? In that case, also, does a decimal representation become terminating when 2 and, when the denominator is divisible by 2 and 5? So these are the questions, I mean, I'm just going to ask some questions which are stimulating, which stimulate your thinking. So please go back and think about it because we have to cover a lot of ground today. Okay. All right. So that was the idea. Our another way of um, convincing ourselves that 0.999 dot 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 is the same as 1. We really need to agree upon this non-terminating decimal form of the number 1 before we accept that the non-terminating decimals can actually represent numbers. Okay, this is really important. All right, we move on to the next one. I have only 10 more minutes. Have we used this symbol before? Next few slides, I'm going to talk to you about some fascinating thoughts about this. Okay, let's look at this. So what I'm trying to say, or again, what I'm trying to convince to you is that you either knowingly or unknowingly used infinity before in your own life, in mathematics or otherwise. And I'm going to try to convince you that most likely you have used this unknowingly, but sometimes you have used it knowingly. How? Let's look at some of the uses of this particular symbol. This symbol that we call infinity is the first use of it is what we call a generalization. Again, like we said, words pop up all the time. What does this word mean? What does generalization mean? Any cases?
Making
Okay.
or saying
Yeah,
something that's applicable to a lot of things in general.
nice.
Like simplifying something into like one big topic.
Mhm. Anything else? Right. I think we can work with those two things, right? One was saying something so that it applies to a lot of things. Another was to simplify, simplification, and both of these interpretations are correct. And this is what I want to tell all of you, that one part of mathematics is to give different meanings to the same words. We are going to encounter so many such words that we use in vernacular in our normal day-to-day life almost loosely, but they become precise when the same words are used in mathematics. So you guys are right. I mean, generalization is a way of saying something firmly, probably and provably about infinite sets. For me, this is really an important thing. Why? Because you can state something confidently about infinite sets without having to follow an infinite process. Let's think about it more carefully. An infinite process should take infinite time, isn't it? The process is never ending. If the process is never ending, can it ever take finite time? The process is infinite. It just goes on. How can it take finite time? If it were to take finite time, it would be a finite process. And obviously a finite process should take finite time. But there is a catch here. What we're trying to do is we are trying to follow a finite process to talk about infinite sets. Isn't it paradoxical that you're only going to spend finite amount of time arguing something, but the conclusion is about infinite sets? This is a big thing. We have got to understand this clearly. Most of the things in mathematics are infinite sets, like numbers and lines, right? Let me give you an example. Let's say we are given a specific isosceles triangle, isosceles triangle, very straightforward. And its base angles are 70 degrees. So 70, 70, and 40, right? And upon some reflection, we realize that the observation is also true for another bigger isosceles triangle. An isosceles triangle, excuse me, has, let's say, 5 meters or 5 centimeter size. And then you make an observation and you find that it is also true for another bigger triangle, right? Upon some more reflection, you come to know that the observation that you have made about that particular isosceles triangle also holds for another isosceles triangle whose base angle is 80 degrees. And soon you realize that it holds for other isosceles triangles as well. Clearly, you know that how many isosceles triangles are there? An infinite number of isosceles triangles. But the observation that you have made applies to all of them. Did we spend infinite amount of time doing this? Clearly not. We just finished that talking about that in, let's say, a couple of minutes or maybe 10 minutes. But we said something firmly about an infinite set. This is a subtle point, but this is very important. I think you have done, even if you are younger, your mathematical journey has started a few years ago. I'm pretty sure that you have made this kind of an argument in the past, right? Whatever applies for this triangle applies for a bigger triangle, even bigger triangle, and an infinite number of triangles. So this is our first use of infinity. We have used this almost unknowingly. Let's look at another one. This is the use number 2. Okay, I'm going to show you an image. What does this image tell you?
Dominoes falling.
Very good job. This is indeed dominoes. I'm going to make it a little more tighter. I'm going to say that's a domino effect that this is showing. And what is a domino effect? You can see that because of the arrangement of the sticks, the specific arrangement of the sticks or pins, once the leftmost, that is the blue stick, falls, it makes every other stick fall. It is not that somehow some stick does not fall. And again, by the flight of imagination, we say that the pattern continues ad infinitum. That is, for an infinite number of sticks. Remember that we can say something about an infinite set of sticks by making one single argument. We did not have, rather we could not have shown an infinite number of sticks falling in that animation. As if by faith, when we see a few sticks fall, and we assume that the same is true for all the infinitely many sticks imaginable, and that they will fall, we have used the concept of infinity. What enables us to do such bold statements? What enables us to argue about infinite sets this way while standing firmly on our feet? Well, one thing that enables us is the observation that the leftmost, that is the blue stick in the animation, just falls on of its own accord. You can see, let's see, it just started falling. We cannot deny that it does not, that it does fall. In fact, we can prove that it falls because we all see. So, such things is what we call self-evident. This particular way of reasoning is almost everywhere in mathematics. Let me show an example. All right, what do you see here? Is there a pattern in what you see here?
Yeah.
What is that?
It's like the outermost border keeps changing colors. It's like first it's like
Right. You know, this kind of an L shape of numbers, like in single color that is there in that image, this blue one, this green one, it's an L shape, right? An inverted L shape, the English letter L. Greeks used to call it a gnomon, or if you G is silent, it's called nomon,
oh yeah.
Gnomon, right?
I've read about that in
Right,
one of
right.
Euclid's propositions.
Very good job. So what is there? How many? What do you see here? There is one orange, three yellow, five green, seven blue. And how many are there? In all, how many circles are there? This is one, this is four, this is nine, and this is 16. So what does this mean?
All the numbers.
I'm sorry?
It's the square of 1, 2, 3,
Right.
and
So these are square numbers, but how are they going to show up? They are showing up by adding odd numbers, right? Right? So what I'm saying is that 1 plus 3 plus 5 plus dot 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 up to, let's say, nth odd number sums up to be what?
I think n squared.
Yeah, 1 plus 3. 3 is the second odd number. That
Yeah.
gives you second square. 1 plus 3 equal to 2 square. 1 plus 3 plus 5 is equal to 3 squared. 1 plus 3 plus 5 plus 7 equal to 4 squared. And then, you know, your suspicion grows, and then you try to see if this is true in general for every n imaginable. We talked about this kind of thinking in a previous slide, right? Do you remember that word? That you go from specific observations and you try.
Generalization.
Right, and you know, even more specifically, it's called induction, right? So we induce something from, excuse me, a specific observation. So what do we do here? We prove that some proposition holds for some small number. But remember, you have to prove that it is so. For example, in this case, we have to prove to ourselves that the square of 1 is 1. And this might be trivial, but if we are not careful here, we are going to have some issues. We'll come to that later. Then what do? We assume that the proposition holds for some integer n. Assume, right? We assume this. We don't prove this. Because we already know that the sum of first n odd numbers is n squared. So we're going to assume that. And then we are going to prove the proposition holds for an integer n plus 1. So this is almost like, I'm tricking you, but this is not. This is a standard way of thinking in mathematics, and we call it the principle of mathematical induction. And again, infinity, we play with infinity here because we are saying something about a first few numbers, and we are going to we're making bold comments about an infinitely large numbers. But we have to be cautious here. Here is a problem. What do you think about this? Is this statement true? I'm sorry, it has to be different. N squared plus n plus 41, not minus 41. Do you think n squared plus n plus 41 is prime? If n is equal to 0, it is 0 plus 41, which is 41, is prime. N squared plus n plus 41 for n equal to 1 is 43, again prime. 2 squared plus 2 is 6, plus 41 is 47. Is that
I
prime?
don't think it's prime because if you have n squared, that means the number that delivers is has to be a composite number.
No, but we are also adding n 41 to n squared, right?
Right.
Yeah, I mean, let me just edit that slide so that we don't go wrong there. Just give me 1 second. Yeah, I mean, I want you to think about what happens is n squared plus n plus 41 prime. Ashwath says that it is not prime. But see, you tried for n equal to 0 or n equal to 1. 1 plus 1 plus 41 is 43. It is prime. You tried for first few numbers and it turned out to be that. All those numbers are going to be prime. And this was a big problem in the 17th century. We had to have someone like Euler who came along and said, hey guys, look at n is equal to 40. When n is equal to 40, 40 squared plus 40 plus 41, which is 1681, it's a square of 41, not prime. The point is that until you went to n is equal to 40, the numbers were all prime. And you still couldn't say that n squared plus n plus 41 is prime. So the point is that, we have to be very careful with the things that we do in induction. So this is the second point where we, our second use of infinity. You guys agree with me? All right, I'm going to go to third one. Yeah. Consider a thought experiment as described by David Perkins in his book. I'm going to describe it as is. A genie, as the story is told, lights a candle at a minute before midnight. All right? It's 11:59 in the night and the genie just lights a candle. Fair enough? After half of the minute has passed, the genie extinguishes the flame. At 11:59:30, the genie extinguishes, puts out the flame. 15 seconds later, she reignites the candle. Right? And again, halfway to midnight, she puts the flame out. This continues as midnight approaches. The time always divided in two, the flame soon leaping up and vanishing faster than we can see. And now the genie asks you, precisely at midnight, will the flame be lit or out? Clearly, some time will have to be spent in just asking this question. But leaving aside the issue of exactly when the question is asked or how long it took, you are still left with some bewildering possibilities. What do you think? What is your answer? Any guesses?
This is kind of like the Zeno's paradox,
Hmm.
wherein uh, a person's crossing a distance, and every time he takes a half step, like he goes half the distance. So in the thought experiment, he'll never reach that point because he's always going half the distance of the distance that's left. So that will be an infinite sequence. But there's a solution to that paradox, wherein the smallest length that anything can go is a Planck length, and you can't go a distance shorter than that. So when the distance between him and the finishing point is a Planck length, he will have to cross that distance. So something like that might happen here, wherein there is a smallest unit of time.
Right. So I mean, you perhaps through your reading would have heard about Zeno's paradoxes, and we'll come to that. You know, it's a very interesting way of looking at it. But yeah, I mean, it's something like this. But what are the questions that are coming to your mind? I mean, Ginny has asked you a question. What is the question? Will the light, will the candle be lit or out? What, what are your answers? Let me ask you that. For now, Arav, just forget that you know about Zeno's paradox for a little while. What is the
Hmm,
question? What are the answers? Ginny is asking you the question. Will the candle be lit or out? What is your
hmm,
answer?
I don't think we can tell whether the candle will be lit or out.
Okay, so Apurva thinks that it's that's not a question that we can answer. What do you guys think?
Can we say it's both lit and not lit?
That's good. I think I like that answer too. You know, Apurva says we can't say. Arav says it's both lit and not lit at the same time.
I I personally think that it's neither of them because saying that at midnight it will be one of them is saying that the amount of time he takes to light and unlight those candles is finite, but in fact because he divides it in half each time it's infinite. So I think it's neither.
That's a good one. I like that too, Pendra. I think, you know, all these are really good answers. One thing that I want you to think about is what if we never get to midnight? Is it possible that we will never get to midnight? And that's what David says. Listen to this. But of course we get to midnight. There has yet to be a midnight that we have failed to get to. Wow. There is a midnight right now that is approaching. Or is it the midnight that is approaching, or are we approaching the midnight? What is staying still? Is it us who is or who are staying still, or is it the midnight that is staying still and we are moving toward midnight? What is this? All these are paradoxes. It's a very paradoxical situation here. One thing we have learned during the story of physics in the 17th century is that nothing sits still. You may see a passenger on a boat and a bird perched on the mast over her head as moving. But from their joint point of view, you are the one who is moving. Who is the observer? Who is moving and who is still? This is not an easy question to answer. Later, in 1905, we learned that one observer may experience time as running more slowly than does another observer. Right? And in 1905, the person who made us see this was Einstein. Questions like this that explore the nature of reality are ancient, and the pursuit of the answers has led thinkers down paths that we have named physics, philosophy, and mathematics. When we say that nothing sits still, we inherently encounter the idea of what? What is the word? Right. It is speed and motion. And that is, the third use of infinity that we have. We had difficulty defining speed. We had difficulty defining motion. Nowadays, you see motion so often that you don't even relate to this idea that motion was difficult to define. All right, and this is the last thing that I'm going to talk about later, but this is the fourth use of infinity. We call it the abstract sets. Well, this is a very, very important slide, but I'll come to that the next because I'm already over time. So Apurva, why don't you just take over? I'll stop sharing for some time and then you can start. Do you want to take this further? This is really an important slide, but we'll come to that later. Is that okay?
You can continue the slide. It's all right.
Okay. All right. So give me a few more minutes. So
Okay.
is that, yeah, okay. Let's think about it. We know that if the number of elements in two sets is finite, then we can compare the two finite natural numbers to compare the sizes of the two sets. So for example, a set has got 10 numbers, another set has got 15 numbers. We can say that this set, the first set is smaller than the second set, right? But how does the situation change when a set is infinite? Several questions pop up in our minds. Since infinity is not a number, how do we compare the cardinalities, that is sizes of those two infinite sets? Are any of the infinite sets the same size? Or are there varieties? If there are varieties, how many are there? Where do we really start? Is there a sort of canonical set that we can assume? These are all very good questions, foundationally good questions. We need to have a shared understanding of these questions. We had talked a little bit about this, and there was a man who spent his lifetime on just answering these questions. His name was Georg Cantor. One of the seminal contributions of Cantor was to provide a framework about how to think about the sizes of infinite sets. Like it always happens, we need something that is given, like, yes, like axioms. In this context, an axiom is the existence of the infinite set that we take for granted, and that is this set. 1, 2, 3, dot, dot, dot. This set is, like you guessed, is the set of natural numbers, right? What Cantor suggested was we try to think of infinite sets by thinking of this set, because this is so simple. Everybody, almost everybody understands this set, that 1, 2, 3, dot, dot, dot. More specifically, we can say that something about the cardinality of any infinite set by using a one-to-one correspondence between that set and the set of natural numbers. This is what he said. Any other infinite set we can compare with this particular set of integers, of natural numbers, in order to say something about that set. This is really very interesting. We're going to talk about one-to-one correspondence, but I'm just assuming that you guys all know one-to-one correspondence, that one from one set, one from another set, and we correspond them. This simple idea leads us to rather consistently state that there are as many odd numbers as there are even numbers, right? Why? Because I showed a one-to-one correspondence right here. I showed a one-to-one correspondence right here. And therefore, there is a one-to-one correspondence between these two. So without spending infinite amount of time, I think I made an argument that said that there are as many odd numbers as there are even numbers. How about these? What do you guys think? This is the set of all fractions. What do you think? The common fractions, are there more fractions than there are natural numbers? You think that there are more fractions than there are natural numbers?
Yeah, I think there are more because between two natural numbers, there are like infinite fractions. So probably a lot more fractions than.
Yeah, so as you make that argument, I'm pretty sure that you're not fully convinced yourself, right? I mean, you're being a little unsure about things. This is the problem that Cantor also had. How would we say this by staying on the firm ground? So let me make an argument, Shashwat, for you. I'm going to argue that there are as many fractions as there are integers. Now, this is really spooky, isn't it? And, and why I'm saying that is by looking back at what Cantor said. He said that the sets are infinite, but I'm going to compare them only by showing the one-to-one correspondence. So here is the deal. Look at this left column, 1, 2, 3, 4, 5, 6, 7, 8. I start with them, but I do something really very interesting. In the middle column, you see the fractions, right? And here is what I do. This is not a one-to-one correspondence. I'm going to click another one and I'm going to ask you to figure this out. But this is one-to-one. I'm going to claim that in the middle column, the set is infinite set of fractions. Do you agree with me?
Yeah.
This is counterintuitive. Like you said, Shashwat, that there are infinitely many fractions. But here, what did I do? This is the little devilish trick that I played on you guys. What I have done, as you can see, I think perhaps it is more clear with the number 5 on the leftmost column. See, 5 maps onto 1 by 4, 2 by 3, 3 by 2, and 4 by 1, right? So what am I doing here?
It's not one-to-one correspondence because it's mapping to multiple.
Right. But what am I doing here? Why is 5 mapped onto those 4 fractions? 1 by 4, 2 by 3, 3 by 2, and 4 by 1.
Because the sum of the numerator and denominator for those 4 fractions is 5.
Correct. What about 4? Look at 4 as well. So 4 is mapping onto 1 by 3 and 3 by 1.
It's the same for 4. 1 plus 3 is equal to 4. That's why it's mapped onto 2.
Right. But 4 is also equal to 2 plus 2. So why is there no 2 by 2 there?
Because that's just the same thing as 1/1.
Correct,
Or
which I have already taken into account
yeah.
above, right? So what I did was, this is a little devilish trick. All I said is that I'm going to look at any fraction that you give me. I'm just going to add their numerator and denominator, and I'm going to get a number, and that number is unique. I'm not saying that I'm going to map that fraction to that number. Look at the right hand side. I kind of flip the model and I just say, okay, 0 by 1 is 1, 1 by 1 is 2, 1 by 2 is 3, 2 by 1 is 4. So by following this process, I'm able to achieve what I wanted to achieve. I have shown a one-to-one correspondence between the canonical set, which is the set on the right-hand side, the set of natural numbers, and the set of all fractions imaginable. Of course, I'm not going to be able to tell you what is the next fraction. Let's say that you ask me, okay, tell me a fraction that immediately follows 7 by 11. Well, that is the successor of 7 by 11, just like 15 is the successor of 14. I won't be able to tell you that. But I'm saying that my middle set is the set of all fractions, and my right-hand set is the set of all integers, and I have shown you a one-to-one correspondence between them. Job done. So however counterintuitive this sounds, this is our current accepted ideal. We are saying that there are as many fractions as there are integers. So when we are arguing like this is where we use infinity. So these are the 4 uses of infinity that I wanted to talk to you about this morning. And although I had half an hour in my mind, I ended up taking the entire hour. But this is how it is going to be, right? I mean, our discussions are not going to be completely time boxable. It's not that easy. And whereas I am also learning, just like you guys are learning, and becoming difficult. Just like, math is all about getting lost in words and mazes and whatnot. It cannot be time boxed. So sorry about that. I think we will perhaps end it here, and then we'll start at the fallout of this in the next session. But yeah, I mean, don't you guys wonder about these things? I mean, I I think this is really wondrous. Do you guys think that I'm tricking you somehow by showing that there are as many fractions as there are natural numbers?
No, I don't think it's a trick because you created some specific order for the fractions.
Correct.
Now, if I tell you a fraction, you can tell me the fraction that not numerically comes right after it, but the fraction that in this order you created comes right after it.
Correct.
Right.
So I gave a whole new meaning to the order, the idea of order. Your idea of order was like, okay, it is immediately next, like 3 is immediately next to 2. Good point. I like you that I did not trick you, but I gave a new meaning to the word order.
Also, you can't do that with, for example, the set of real numbers. I
Yeah,
in my, do you think it might be possible to create such an order? I'm not sure. Is it possible to create such an order for real numbers? It's an interesting question.
very good point. I think, it's a food for thought for all of us that what we can do for fractions can we do for real numbers? And this is a food for thought for all of you guys. Now, what is there in real numbers that is not in rational numbers? What is
Irrational
that?
numbers.
Right. Now, irrational numbers are a big beast. And I can tell you that there are way too many irrational numbers than there are rational numbers. And how many irrational numbers do you know?
Mm,
What's your favorite irrational number?
I don't know, pi.
That's very
E.
good. So you like pi, you like e. I like square root of 2. I like third root of 3. I like hundredth root of 71. And the list is just endless. I think, this is really a food for thought that the number of irrational numbers just far, far more than the number of rational numbers and integers.
I have a question.
Please go ahead.
So this would imply that because there are infinite normal integers, that there are also infinite irrational numbers.
Correct. Yeah, I mean, irrational numbers are obviously infinite, right? Like I just said, right? Uh, take any number and take all the roots of it. What are those numbers going to be? What is going to be cube root of 3? Is that going to be a rational number? What's going to be fourth root of 4 or 71st root of 35? I mean, it just like, when you think about it like this, it actually makes you squirm in your seat. It becomes very uncomfortable. And
Uh,
Cantor actually started asking this such questions, and then, you know, then this kind of thing came forward. Yeah, I'm sorry, somebody was saying something.
Yeah. So I had a question last class, but I didn't really have some time to ask it.
Go
So can
ahead.
there be, so can there be sets of complex numbers?
Cool.
Yeah, I mean, you open up another kind of, big thing, we are limiting to real numbers. But yeah, I mean, complex numbers are a paradise of their own. Um, right. I mean, the infinity of complex numbers is an infinity that we need to reckon with. We need to wrap our heads around that. But I think for this discussion, we are limiting ourselves to real numbers. And you might wonder, what has all this to do with calculus? I want to learn calculus. Well, the problem is that you can't pluck calculus out of the rest of mathematics and say that, okay, I'm going to learn that. You will soon realize that everything in calculus relates to everything else in mathematics. And that's why we are spending some time on this. So I apologize to you, Apuru, for stealing the thunder. Um, but this was important, I think. So we'll start with some of the fascinating topics that you have to cover next time. Um,
Okay.
I do want to, yeah, thank you for that. And I do want to uh, say that, okay, we have managed to end it in time. If anybody has any questions, please go ahead and please discuss that on our group as well, whenever things come to your mind. All right. I'll stop sharing and then I think, yeah. Cool. So I think it's 8:35 our time, 9 o'clock in India. So we'll stop